Hello. This lecture will cover pages 272 through 277 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 9F, Power Factor Correction. Starting on page 272. When apparent power, that's kVA, is greater than the working power, that's the true power measured in kilowatts, the utility company must supply the excess reactive current plus the working current. This results in a lower and lower power factor, which costs the utility company money. If an industrial load's power factor is too low, the utility company will require you to improve the power factor by adding power factor correction capacitors to your plant's distribution system. The following is an example of how engineers can correct for a low power factor in a plant's distribution system. Remember how power factor works. Whenever you have a lot of resistive load compared to reactive load, the power factor approaches 1. Whenever you have a lot of reactive load compared to resistive load, the power factor approaches 0. So the power factor falls somewhere between 0 and 1. It's just a number. So a lot of manufacturing facilities have a lot of motors, a lot of reactive load. And that reactive load, even though in terms of true power, it'll take energy, but then during the negative half cycle of the sinusoidal waveform, it returns it. The utility company has to come up with this tremendous amount of energy to supply it across the grid during the times when the company is borrowing the power, if you will. So remember I told you in class, it's like I want to borrow $1 million off you, so lend me $1 million and I'll pay you back tomorrow. Well, you have to come up with $1 million today. But you say, well, in a 24-hour period, you're going to break even again, I'm going to pay you back. Well, the utility company still has to come up with this power. So what they make you do is they make you correct that power factor. Get it closer to unity by offsetting those inductive loads with some capacitive loads that you supply. So here's an example. Assume that an industrial load has an impedance of 100 plus J 130 ohms, which is reasonable. At a frequency of 60 hertz, what value of capacitance would it take to correct the 0.61 lagging power factor to a 0.85 lagging power factor? The electric company wants you to improve that 0.61 lagging, we know it's lagging because it's inductive, to a 0.85 lagging. So here's what we have. Here's the circuit, here's our load. We put a capacitor in, and I'm going to show it in series here. There's capacitor compensation or correction capacitors you can put in parallel, but we're going to put this in series, make the calculations a little easier to understand. So let's take a look at what we have. This is what we have. The power factor we know is the cosine of the angle of the impedance. Well, I can find that angle. The angle is just the inverse tangent of 130 over 100. It's just the polar magnitude of this. It's the polar phase of this. So I can see it's 52.43 degrees. If I take the cosine of 52.43 degrees, I get a 0.61 lagging, and that's what they give us up here. I want to work backwards and find what this angle is from this 0.61 lagging power factor. Okay, so I'm just taking the inverse cosine of 0.61, if you will. So the inverse cosine of 0.61 gives me the 52.43 degrees. So down here, all I want you to look at here is here's my inductive quadrant. Here's my capacitive quadrant down here, the fourth quadrant. And I'm drawing a vector from this point out to here. And the only thing I want you to look at is that vector right here that goes out. Notice it has a real part of 100, which it should. And it has an imaginary part of plus J 130, which it should. And there's the angle 52.43 degrees that goes between. So the only thing we're looking at is this larger triangle here. Now what we've been asked to do is correct this power factor, correct this triangle, if you will, to make it a smaller triangle, to make it a smaller angle, to a 0.85 lagging power factor. Well, the corrected angle The corrected angle is just the inverse cosine of 0.85. So that angle is 31.8 degrees. So if we put another triangle in here and I show a vector gone out, I don't know what this point is right here, but I know the angle is 31.8 and I know the real part's 100. So what I have is this larger triangle, and what they want me to correct it to is this smaller triangle. They want me to correct it from 52.43 degrees down to 31.8 degrees, and that's reflected in the power factor. Well, to do that, I think you see here that what we have to do is we have to deduct this much inductive reactance. How do you get this point down to here? Well, you add a capacitor. You add a capacitor up here. That capacitor basically puts a triangle down here. So I need so much X sub C, so much capacitor reactance to offset all this 130 ohms of inductive reactance. Well, how much do I need? I need this much right here. I need from here to here. Well, how do I find that? Well, I just go back to this final value, this final triangle here. If I look at this triangle here, I know this side here is 100. I know the angle. All I have to do is find this opposite side here. I call that X sub L corrected. This is where I want to end up, to X sub L corrected. So if you look down here, I take the tangent of 31.8 degrees here. It has to be equal to the opposite side over the adjacent side. So this X sub L corrected is plus J 62 ohms. This is 62 ohms. I'm just going to talk in terms of the reactance here. That's 62 ohms. I have 130. So this corrected amount here has to be the difference between the two. So X sub C to correct, I show it down here because it's a pure capacitance, but what it's going to do in its net effect is this vector here is just going to subtract from the top up here. Well, I take the 130, which is what I had originally of reactance, inductive reactance, and I subtract out the 62 because that's what I end up with. And it tells me I need 68 ohms of capacitive reactance to offset this down, to bring this point down to here. So my capacitive reactance to correct is what I call it, is this minus J 68 ohms. Now I don't care about the minus J part, I just care it's 68 ohms. X sub C is 68 ohms. So if you take a look, you know what X sub C is equal to. It's 1 over omega C, which is 1 over 2 pi FC. Solve that for C. C is equal to 1 over omega X sub C, or 1 over 2 pi Fx sub C. I know X sub C from the previous page. It's 68 ohms. It's 68. I make the substitution here, either with the frequency or the radian frequency, the angular frequency, and I get capacitance is 39 microfarads. 39 microfarads is the capacitance needed to correct the power factor from the 0.61 lagging to the 0.85 lagging. It's just right-angled trigonometry. That's all it is. Now, you might say, well, gee whiz, 39 microfarads. That's nothing. This is a high voltage capacitor. The physical size of these power factor correction capacitors are measured in feet, not inches. They're not little tiny guys. Now sometimes these capacitors are placed right outside the facility in a shed because they're pretty big. Or sometimes they're right inside the building. But sometimes they have these capacitors on individual motors to correct the power factor at the individual load. So they can be placed many different places. But what I wanted to show you here is that basically all we're doing is using a little right-angled trigonometry to show you how you can add capacitive reactance to offset the very low power factors, inductive lagging power factors, if you will, to get them closer and closer to unity. And what that does is it shares the energy between these points here, the reactive power. And the utility company doesn't have to supply that extra power during those half cycles. And that concludes this lecture on power factor correction.